Okay. Okay, I think we're back. Let me know if this is a okay. Thank you. Okay, let's see if this works better. Okay, so as I was saying, the goal is to detect that a given expression in your code does not have the type that the programmer said it would have. Okay, so the idea is to catch bugs before we even run the program. Okay, and let me give you an example. So if you were to write Haskell code for the head of a list, you could have something like a list where the length of list is greater than 0. Okay, and then you could return an integer. So the idea is that you could have certain refinements on the types. Download. Okay, did we just crash? No. Okay. Maybe. Okay, sorry. Technical issues. So I was saying we can refine the type list with a certain predicate. In this case, that its length is greater than 0. Okay, and the idea is that we ever call head of an empty list. This should be a type error, and we shouldn't even compile this code. Okay, but of course we can improve this. So we could represent the size of a list that returns an integer, and that integer is equal to the length of list L. Okay, so here we could even accept any list, and this is the first case we've seen of a dependent type. Okay, so refinement types are those that have refinements, so have these predicates. Okay, and among the refinement types, some of them, like this one, is dependent because the result, the type that the function returns, is dependent on the value of the input. Okay, so the return type doesn't work on its own. It only works when you have an input value. Okay, so this is the brief introduction to what refinement types are. Now the trick is to understand what can we write here. Okay, and in some languages like Clean, we can write anything you want. Okay, so there's no restrictions to what we have here, to what the predicate is, as long as it's in the overall language. Okay, this would be similar to what you could represent in Idris or Coq or some other more powerful language. Although then you have to deal with the universe level. Okay, so there are always some restrictions there. But the tutorial that we're going to follow, it's not really about all the refinement types, but about liquid types. So liquid types are those in which this predicate can be statically verified. Okay, so for that we're going to use something like an SMT solver to prove that this is true in a given context. So we are going to limit the language here to the language that can be verifiable with its own theories. So if we go back to the tutorial, okay, it's going to be this language, and you can learn a lot more here about what are the semantics and so on, and we'll go into a little detail here. So let's open here a Python interpreter, and we can try to import Z3. Okay, and now it's the time where I'll answer the question about what kind of things can I use Z3 for. So the way you work with Z3 is that you create a solver, okay, and then you can create variables. So I'm going to create x will be an int, and I'm going to name that integer x. Okay, so usually, so this is the name in Z3. This x outside is the name in Python. We usually have the same for both to make it easier to translate what you're doing in Python to what Z3 thinks internally. So we're using the Z3 bindings in Python, which are in this Python dependency. So we just pip install -r requirements, and you should be able to import Z3. Okay, and it should work in any operating system. So right now I have a solver and I have a variable. Okay, and I can add to my solver. So you can add several statements. You can add that x is greater than 0, for instance. Okay, and now you can do s.check. That's going to show that if it's possible, that means if there are values for x in which all the predicates are true. In this case, that value is greater than 0. Okay, and I got sat, so I could even get z3.sat and sat, which means it's impossible, there are no values, we'll see an example, or unknown, which is the Z3 is not capable enough to prove that, or it timed out trying to get this. So this is not something you can compare directly to Coq or Lean or other high-level programming language in which the human has to prove. This is completely automatic, but has more restrictions. So some high-level languages, for instance, Daphne, use SMT solvers, including Z3 underneath. And in the cases where it was possible to get this value, I can do s.model, and it will give me, okay, with x equals to 1, this was true. Okay. So now let me create a new solver and add that x. So because this is a new solver, x greater than 0 no longer applies. So I'm going to add that x is greater than 0 again, and that x is smaller than 10. Actually, that it's smaller than -4. Okay, and in this case, it will be impossible. Okay, so it's unsatisfiable. And if I do s.model, I will get an error because model is not available. We only get a model when it's possible to add the value. So the idea is that we can use this SMT solver to check if the types are correct. Okay, but in order to go from a programming language to this expression in Z3, we will need to implement that part, and that's what we'll cover both in this video, and it's what the tutorial also covers. Yes. Just a quick note. So in for instance, if you consider Daphne, which is a verification language for software, it does everything automatically using SMT solvers, but you can find points in your code in which SMT solver does not have enough information, and in that case, you need to add the information by hand, which is more towards the Coq approach, in which you add little by little so it can work out the proof. So I think it's the crunch. There are a couple of statics in Coq which also use SMT solvers underneath. And Lean, which is another language similar to Coq, also makes a lot of usage of SMT solvers. And one of the authors of Lean is the same author of Z3, Leonardo de Moura. So these tools can be used in high-level languages, but they're more restricted. Okay, so I think that's the point. Okay, so we've seen a little bit of Z3. So I think now it's the time to. So maybe we'll do this for another 15 or 20 minutes. So right now we don't have anything, right? So the compilers I write, usually I start with a representation of an AST, okay? And this is where Haskell or ML programmers really shine, because their languages are really designed to handle these scenarios, right? So they're really good for compilers. Python is a general purpose language which we can use for everything, but I'll have to admit right now Python doesn't support ADTs. So it will in the future. There are a couple of Python improvements that will add that, but right now we will implement AST as in an object-oriented way. Okay, so in the past I've done things like this would be my AST node, and I would, for instance, have a literal, which, for instance, if I do let a equals 1, 1 is a literal. It's the actual number that I write in the language. So I would extend the node with all the details that a literal has. And I also have done something like type, which was a string, and children, which was a list of nodes, and type would be a string. And in this case, I would just have this class that would represent all the nodes, and then I would have to, when I want to pattern match, I would just do an if, elif, and so on for the type. While in the previous approach, which is what we're going to use, I would have a lot of ifs with the existence, like the Java is instance of. So I'm going to start with the liquid term. And now let me go back to the tutorial, and I'm going to be representing all of these languages. Okay, so I'm going to focus on the predicates first, which is what I'll call liquid term. And we could have variables, literals, so Boolean literals, integer literals, and then we could have a lot of things. So I'm going to abstract all of this to the same one, which is an application of a function. So I'm going to abuse this version to include both uninterpreted functions and all of the other native functions that you have, for instance, in Z3. So I will have three types of liquid terms, or four. Draw int. So this will have a value, which will be an int. I actually need to define the constructor. Okay. I will have a bool, pretty much the same. Let me just add type annotations. For those of you that haven't seen Python in a couple of years, this might be new. Okay, then we have the variable. I'm going to call liquid var, which has a name, which is a string. Okay, and then the last one, which includes all of these approaches, which is just copy an application which has the name and it has the arguments, which is a list of liquid terms. This list, it's the typing list, which is just useful for type checking. Self.arguments. Okay, so it's not defined, didn't print. Okay. Okay, so right now we have the AST that represents those predicates that we can have inside types. So we're just talking about the expressions in the types, not the language. That would be just a term. This is a liquid term, which is what I call what's the language that's in the predicates. So now let me create a folder. With tests. So let's just add a first test. We're going to use PyTest. So let me just call this test A, assert true, and test. Discover tests. Let's enable. We're going to use PyTest tests. Okay, and now we can run our test, and it passes. So PyTest is a really simple to use framework. We just create a function called test underscore its name, and we're going to assert. So as a first example, we can see if a predicate is satisfiable. So we could have the predicate, it's a literal, it's a liquid app. Let's call it greater, and it has the greater, I know it has two arguments, which is the liquid var called x, and let's say it's the liquid literal int 0. So this is something similar to the example we've seen. We need to import sprite liquid app, liquid var, and liquid literal int. Okay. You're complaining because maybe I don't have here the sprite liquid, sprite core, not. Okay, now it makes sense. Yeah, in Python 3 these init files are no longer mandatory in subpackages. So now we're going to test this function, the isSat. Okay, so this will translate our liquid language into Z3 and return whether it's satisfiable or not. So we're going to create a package called VC, which stands for verification conditions, which will be a more complex version of isSat that we'll see probably next time. So, for instance, we will want to see something whether so whether this type is a subtype of this type. So this means that all the values that belong to this type also belong to this type. And right now the only value of x that belongs to this type is 5. And 5 is of type x greater than 0 integer. So we will want to translate this into something like a predicate, and then we will use Z3 to solve that. So right now we're just going to implement this function whether p is satisfiable or not. So I'm going to just call it sat.py, and it's going to receive a liquid term and return a bool. Liquid term, and here we can sprite.vc.sat import isSat. So you're going to implement this function. We should run this and we should have an error. And that's the error, and we can see more detail about it. If we select here a test log, we have here all the details that the function returned none, and none it's not true in the assertion, so it failed. So now let's, inside this function, let's implement it. So this is the place where we're going to import Z3. We're going to need the solver, int, bool. So these are the constructors of variables, and I think that's it. So we are going to create a solver. We're going to add the Z3 version of LT. And we're going to return if s.check equals sat, which we also need to import. Okay, so we're going to create a solver and check if this is possible. But we need to convert our liquid term, the AST we have, into the Z3 version, which will actually be a mixture of Python and Z3 bindings, because the bindings for Z3 in Python are very Pythonic, so they're actually very readable. So we're going to call this translate function of LT. We're going to receive a liquid term. We're going to return, well, for now we'll just leave it as any. We can refine this later. So this is where we will have a lot of if is instance LT of liquid var. We're going to return an int. So this is the z3.int with lt.name. Okay. So I think this will have a bug that we'll come back to. So it's not really important right now. If it's not a var, it could be a liquid literal int. Liquid literal bool and int. We also liquid literal liquid app. And if it's an int, we'll just return the lt.value. If it's a liquid literal bool, we'll do the same. We'll just return the value because both of them are valid in Z3 bindings. And the other scenario is a liquid app. And if it's none of these, we'll just assert false, so we'll never get here. So this is the more complex scenario. So I'm going to create here built-in functions. So this function, I think it's one that I used, will return a lambda that receives two values and returns x greater than y. Okay. So this just allows me to not use the same symbol in our language as the Z3 version. For instance, in this case it's the same, but in some other examples it's not necessarily the same. So we have here a translation layer. So we're going to create a function which is the built-in functions of lt.name. Then we're going to translate each argument. So new args is the translate each argument for a in liquid app dot arguments. Going to return f of an args. Okay, so for those of you not really familiar with Python, this means that if this is a list, we'll pass each element of the list as a parameter. So if this is, in the case of greater, we will have two arguments, so f will receive two arguments, which is the x and y. So we have here our little translation tool. So we might run our tests now, our single test. Okay, and it passed. Okay. But we still have a bug, and we can't have another example here. Can anyone guess what the bug is? Just add here. I'm going to change this to another example. Okay, so now our example is x equals to false, and I want to know if there's a variable x that can be equal to false, and the answer should be true, and the value in which this is true is x equals false. Okay, so this is a quite straightforward example. So if we go inside this sat function, the translations that our variables are all integers. Okay, and that's an issue because not all our variables might be integers. We might have integers, booleans. Z3 also supports some floating points and some strings. So this construction might depend on the type of the variable. But right now we don't have the type. That's because we also need here a context, which right now will be a dictionary between two strings, and next time we'll cover this. This is the last thing we'll do today. Okay. So this dictionary will say that variable x is of type bool or int. Okay, and right now this will be a string, but in the future we'll have your representation of the type. So our sat will actually receive here a context of x as a bool, while the previous example received an int. We're missing this. So there's a bug somewhere. No, just okay. This test is passing. This one is not. It's correct. So now our translation layer also needs to have the context. And the same in the recursive call. And now here I can say if the type in the context of this variable is bool, well, if it's int, else assert false. So this is where pattern matching in ML or Haskell would shine. This is a bool, because you wouldn't need to have this if mass for pattern matching. So if we go back to the test and run it again, okay, we're missing this definition, so we actually need to have more so we're going to define this one and rerun the test. Okay, and it's working right now. Okay, so a few things to finish this this step. Right now we need a list of functions that we support in our liquid types, and we have no type checking in our liquid terms. So if I saying that x is an int, this will fail the test, but will not we will not detect this. Okay, it will be just the well. Well, Z3 even accepted this. Let me try the other way around. So let's say that a bool is greater than 0, which which is a bit strange. Okay, so in this case it will fail, but it will also fail if we pass 3 arguments to this function, right? So saying that x is greater than 0 and 0, so something like a Lisp version of greater than. So this will also cause some errors in the code, not necessarily detected by our code. Okay, so I think that's enough for our first version. So we've seen so far half of the second chapter. So if I go back here, so we've implemented an AST for this, and we've translated it to an SMT solver, which corresponds to this part, or at least part of this part. So we will still need to add support for more operators, as well as this constraint, which adds the for all, for the implication, which will allow us to add that context, that x is a boolean or an integer or something else. We'll have that here. Okay. Right now we only passed as an extra argument, a little bit of cheating, but in the future we'll add support for this, and we'll have some more interesting examples like this one. Okay. I don't know if anyone has any last questions. Okay, so thank you, and I'll see you next time.